Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to talk about an FM transmitter and the radio wave that it generates. So let's first look at what they say a radio wave is. This is from Wikipedia. Radio waves are a type of electromagnetic radiation with wavelengths in the electromagnetic spectrum longer than infrared light. They're just telling you where it is in this spectrum. They have frequencies as high as 300 gigahertz and as low as 3 kilohertz. And their wavelength, look at this, a wavelength at 300 gigahertz is only 0.039 inches, 1 millimeter, but it can be as far as 62 miles at 3 kilohertz. Can you imagine a wave of any sort being 62 miles? Like all other electromagnetic waves, they travel at the speed of light. Now this is a drawing, there's lots of them on the internet. I didn't put the reference, but it's an electromagnetic wave. It's something that's moving in this direction at speed c. It has a magnetic field, it's red, it's horizontal, and is moving back and forth at some rate. Well, the rate, that's the wavelength. And it has an electric field, the blue one, which is vertical. Actually, they're saying they're just at right angles to each other, and that's the way they understand an electromagnetic wave. For the life of me, I don't know what's causing these changes. I don't know whether this is there's a particle that's moving up and down, or whether this is just something that has different amplitudes of some sort. Hard to explain, but that's what they say a radio wave is. In fact, that's what they say visible light is, and so on. Well, it wasn't long ago, and I had a video about the candle and the light bulb, and this is a slide from that one, and it was explaining how atoms emit light for a light bulb. As a particle activates this, an electron jumps, falls down and releases energy, and the energy is in the form of a photon, not an electromagnetic wave. Of course, when you look at what a photon is, it's a particle and a wave. It's two things. I'm not sure which one. I know this is one from a light bulb, but it's still in the electromagnetic spectrums. Got two answers. I'm not sure which one I should be saying is the right one. Now let's talk about the speed of the electricity, for example, in the transmitter, the FM transmitter. The word electricity refers in general to the movement of electrons or other charge carriers through a conductor. Okay, so we have electrons through a conductor, just like we have in the FM transmitter. The speed of this flow has multiple meanings. The first one is that the signals or the energy in that circuit travel as waves, electromagnetic waves. Now, I studied EE in college and the physics part of this in college, and I don't remember them telling me they were maybe they said it. Of course, that was back many years ago. That's what they say is there. It's totally missing in my history. But it travels at 50 to 99% of the speed of light. Now, as a side point, when you put a scope on a point in a circuit like this, you will see that things move pretty fast. The signals through the electronic circuit move fast. So the justification for the fact that they're moving fast is to me is just by experience. The prop delay of signals through the circuit doesn't take long at all. It's in nanoseconds and microseconds. But then they say the electrons themselves move. They don't but they say drift much more slowly. In fact, in this same article later, in copper wire, an electron moves at 3.2 meters per second. Electrons are moving slow, but the waves are moving fast, and I don't know how to split the two. So this is kind of what they're saying it is. I didn't put the wave in here because I don't know how to describe that wave. But assuming we got electrons coming out of the battery and powering the circuit and sending signals, which I contend are electrons being sent to that antenna, and somehow that antenna magically produces an electromagnetic wave. Or maybe it's a photon, it's not clear. And then somehow when that wave or photon hits this, it produces electron motion in the antenna. Now there is photoelectric, and there's photoelectric effect, and there's the photoconductivity ideas. Both of those work at high frequency, whereas the radio wave is working at low frequency or very long wavelengths. Not clear what physical property they would apply to this, but there you have it. Somehow electrons hit the antenna, you get a wave, you get a photon, and it all works, so they say. So let's look at the transmitter. There's a microphone here that you speak into that changes resistance value as you talk. It is part of an oscillator that is working at for example, 106.3 megahertz is ESPN here in Boca Raton, Florida. And it's oscillating, creating a wavelength of about 3 meters, 10 feet. And then it's fed into an emitter follower, which is a unity gain amplifier, and then another inverting amplifier with filtering, finally to the power amplifier Q4, which feeds the antenna. That's basically the circuit, and I'm going to concentrate on this trail end here. In the particle model, the TPM and the G1 particle, from the transmitter, the battery releases G1 orbitals. So G1 it's releasing G1s, and they were orbitals moving at a very high speed. And they move into from the battery into the circuit. So the electrons, they say, move at 3.2 meters per second. I'm saying no, the G1 particle, which is the replacement for the electrons moving at speed c, it moves that in the circuit, and then the G1 particles finally get to the antenna. They're scattered into the atmosphere. They propagate through the atmosphere. They get to the radio, into the antenna, where it's the audio signal is detected, and the G1 particle actually ends up going through the battery there, or the power supply. I talked about the speed already. When the G1 particle enters the circuit, it flows through the wire and the components at speed c. It's guided by the internal G2 force field. Now you remember, every object in the particle model has a G1 force field around it and a G2 force field around it. And those force fields are holding the atoms and molecules together, and as a consequence, they guide the G1 particle through the conductor. It guides through it, and in fact, they can even take a right-hand turn and stay in a right-hand turn. You can see it inside the circuit, an actual layout. It does not hop from hole to hole like the electron does. That's why it goes so slowly. As in the particle, in the real model, or the one that they explain, the electron is a free particle in the copper wire, and there's another atom next to it that has a missing electron, and so the electron jumps into that missing spot, creating a missing spot behind it, and it kind of hops from hole to hole. But the G1 particle doesn't. It is flowing through the conductor wire freely, just like an asteroid flows through our galaxy. And it doesn't. We don't have an EM wave. We don't have an EM wave at all inside the wire. Okay, so let's talk. We're going to talk about the bias point of this one. I mean, it's a simple point. You've got a DC battery around that bias point, and that sets a point on this transistor. Got to operate that transistor in the linear region. If you operate it outside that, you don't get a linear gain. You'll get distortion. So it's got to be biased at a specific point. And the G1 particles flow through this transistor and around, and they get DC blocked by the C1. So you have the particle flow through the Q4. They're blocked. Capacitors do not pass DC, so only the AC component. This is a pulsating DC signal. And then it goes to this balun is an impedance matching transformer to match the output impedance to the antenna impedance and out to the antenna. That's the points of what we're trying to concentrate on here. So at the G1's at the collector. I can look at this several different ways. First way is that this is the voltage and a bias point. And as you may remember, in some cases, I generally assign each G1 particle a voltage. So I'm not doing any math here. It just sets a DC level. And if you were to put a scope on that point at the collector, you would see an AC signal like this with a DC bias, but you don't see, with the scope, you don't see the particles. But the graph can also be looked at as a number of G1s. And the bias point says you're going to have this, when you're biased and there's no analog signal, no voice, it's going to constantly have that level of particles flowing through it, G1 particles. But when someone speaks into the mic, an audio signal, and this is at an audio rate, this is the wavelength of your voice, my voice, and it'll turn it on higher, put it in higher and higher, and putting out more and more particles, and then lesser and fewer, creating this stream of particles that have a peak and a valley and a peak. So this is the signal that I would expect to see at the transmitter, and this is the particle representation of what's going through the Q4 transistor. Well, then when it's DC blocked, that bottom half is clipped off, and you're left with this hitting the antenna. And it's just a stream of particles, G1 particles, flowing into the antenna. Okay, now this stream of particles, they're going to hit the atoms in the antenna. They can pass straight through, by the way. They can pass straight through and go right out the end of the antenna, giving you kind of a directional view of where they're going. Or they can hit atoms and scatter in all directions. Or they can get trapped. They could actually get trapped and get locked into, if they happen to be at the right speed, right direction. They could become an orbital of the antenna. Maybe not for long, but there it is. This is not an electromagnetic wave that is being emitted from the antenna. Okay, I'm trying to find out where I'm at. So that's the wave. This is the wave that's being transmitted through the atmosphere. And it hits the radio. I'm not going to go into the radio much, except that the G1 particles enter the antenna, get captured by this, and are guided through the wire by the G2 force field. It's a tunable circuit. You can tune it to 106.3 megahertz to get ESPN radio here at Boca. And this is a simple one transistor radio, which gives you a little bit of gain through your headset. So in the case of the particle model, we have G1s coming out of the battery, G1s powering the circuit, and when someone talks, it modulates the frequency, sending getting a modulated signal at Q4, which gets sent to the antenna. It gets scattered in all directions, including the direction to the radio, and it's got this waveform. These are streams of particle moving at speed c that have lots of particles here, defining the wavelength in the valley. They enter and get trapped by the antenna and detected in the radio. G1s at the beginning, G1s all the way through. So no energy required to create a photon, no magic where you're sending electrons into the antenna and it makes an electromagnetic wave. So compare the two. Compare the two. Today's science says it's this way. Particle model says it's this way. It's quite amazing that how simple this is and how complicated this is, and not, in my mind, not well understood. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.